Chapter 3, Part 1, Section 3.1, Chemical Formulas. This is all about taking a chemical formula and understanding what is in that chemical formula. Okay, nomenclature and formulas. Chemical nomenclature is the systemic approach to naming chemical compounds. So what are the rules that we follow in order to name a compound? Chemical formulas combine elemental symbols and subscripts to represent different compounds. So here are two examples of chemical formulas, Fe2O3 and O2. Those are both examples of chemical formulas. Okay, we'll get into the nomenclature after a little while. Chemical formulas show a formula unit of a compound. The symbols, the elemental symbols, identify the element present. The subscripts, so if we have something like B sub X, tell how many of that atom, how many X tells how many B is present. Parentheses, when they are used, display how many of this groups of atoms are involved. So as an example, if we look at Ba3PO42, this contains 3 Ba atoms. Okay, that makes sense. But then we've got this parentheses around PO4. So we've got 2 phosphorus atoms and 8 oxygen atoms there. Okay. Now, determine the number of atoms of each element that are present in one formula unit of MgClO3 and NH4 SO3. Well, this is kind of easy. We've got 1 Mg. We've got, well, this 2 has to apply to what's in the parentheses, so 2 Cl. And then we've got 6 oxygen. Okay, for part B, we've got 2 applied to anything that's in parentheses, so we've got 2 nitrogen. We've got 8 hydrogen. We've got S, and we've got 3 oxygen. That's everything that I just said. Okay, compounds exist in different forms. Okay, a molecular compound exists as individual particles made up of bonded atoms, known as molecules. So when you hear molecular compound, think a molecule. Now, one formula unit of a molecular compound represents one molecule. And this is a little bit subtle, but I think that you'll pick up on it as we go through some examples. Molecular compounds, this is a very important descriptor of a molecular compound. They contain non-metal atoms bonded to each other via covalent bonds. Okay, so make those two terms interchangeable, molecular and covalent. A molecular compound has covalent bonds. We'll get into that later in the class, but molecular, I want you to think non-metal, covalent. Molecular compounds are also called covalent compounds. See, there we go. Just like I said, we get into it later in the class. Done. Okay, compounds exist in different forms for ionic compounds. Ionic compounds exist as extended 3D lattice structures of atoms. So what that means is that if you have like NaCl, table salt, well, that's sodium and chloride, but you're not going to have a single Na and a single Cl present. Instead, you have a lattice, you have this complex network of these atoms. So these atoms, so there are no distinct molecules in an ionic compound. A formula unit only represents the ratio of atoms. It's not representing the molecule. Okay. Now, these atoms are held together by ionic bonds. And so what I want you to do is think ionic compound and think you have metal atoms and non-metal atoms, which is indicated here. Now, here what we have are a couple of different representations. We've got atoms of Ar. Ar, argon gas, is an example of a noble gas. What argon likes to do is it likes to exist as independent atoms. It doesn't need to bond with anything else. Molecules of Br2. Br and Br like to pair up with one another. So Br and Br, they pair up with one another. Awesome. 2 Br come together to make, well, one molecule. Now, what's shown here in this option C, in this last one, is there we have formula units of NaCl. So this green sphere is Na, and the gray sphere is Cl. Well, if you were to break this all down, you don't have just one Na and one Cl. My A is not written particularly well there. Instead, you have a ratio of one Na to one Cl, but you have tons of them in this network together. Classify each of these as an ionic or a covalent molecule, or a covalent substance. Okay, I'm going to go ahead and let you pause if you want to. Now, in order to do this, what we want to do is we want to determine where these different substances are, where these different elements are on the periodic table. Remember, an ionic is metal plus nonmetal. Covalent is 2 nonmetal. Or covalent / molecular is 2 nonmetal. Okay, so calcium is a metal, chlorine is a nonmetal. Therefore, this is ionic. Carbon is a nonmetal, chlorine is a nonmetal. So this would be, I'm going to say, cov-mol. Hydrogen is a nonmetal, oxygen is a nonmetal. Again, cov-mol. Those are 2 nonmetals. Remember, hydrogen's on the far left-hand side of the periodic table, but it's kind of an outlier, and we'll learn how it's an outlier later on as we proceed through the semester. The last one, Fe, which is iron, that's a transition metal, almost smack dab in the middle of the periodic table, and oxygen is a nonmetal. So we've got an ionic compound. So, molecules of elements. Some elements are never found in nature as individual atoms, but occur as small molecules containing 2 or more atoms. So from left to right, we've got 2 Cl, 4 phosphorus, and 8 sulfurs that kind of pair up with one another. Now, a couple of very specific examples of these that I want you to commit your memory to, and I'll tell you from my own experience taking AP chemistry as a senior in high school, Mrs. Jones was my teacher, and she was a fantastic teacher. I still feel awful that I failed the AP test, but she had a picture on her wall, and it was a guy, it was a drawn picture of somebody, and they looked like this. They had eyes, nose, like a mustache and a mouth, and maybe ears. And this person's name was H. Broncliffe. And that was kind of used, or that was just there for, heck, this is a really easy mnemonic for you to remember. Which are your 7 elements that form diatomic molecules? So these, like hydrogen, what it likes to do is it likes to pair up with another hydrogen to form H2. Bromine likes to pair up with another bromine to make Br2. Oxygen likes to pair up with oxygen to form O2. Nitrogen and nitrogen, N2, and so on. Okay, and cliff, the end of there. Okay, allotropes are different molecular compounds of an element, different molecular forms of an element. Oxygen allotropes are molecular oxygen is O2, and then another homonuclear molecule is ozone. That's nothing but oxygen, but it happens to be 3 oxygens. There are carbon allotropes, graphite in pencils, nanotubes, which can be used in medicine as well as many other applications, and diamond, and it's just the network of carbons that have all formed together. So that kind of sums up everything that you need to know about nomenclature, or not nomenclature, but looking at a formula and extracting what is that formula, or what is in that formula. I hope this helps, and we'll proceed on in section 3.2.